If a Minkowski spacetime contains a compact region omega that is isomorphic to r cross sigma, where sigma is a threefold manifold of non-trivial topology whose boundary delta sigma has a topology isomorphic to s squared, and if furthermore the hypersurfaces of sigma are all spacelike, then the region omega contains a quasi-permanent intraverse wormhole.
Is that it, Will?
Fill my the science guy.
So what is a wormhole? To discuss them, we'll need two previously covered topics. Time dilation? See? It's called time dilation. Notice that our clocks are the same. Now when I run really fast, like this, now, time passes slower relative to observers, sitting still, like Robert here. See? Our clocks are different. Wow! And light cones. This here is a light cone, of science of course. The top half of the cone represents all points in space separated by time. That's everywhere you could travel. The bottom half of the cone, however, represents all of those points in the past. That's everywhere you could come from, assuming you don't move faster than the speed of light. A wormhole is a hole connecting two distant points in space-time, allowing objects to pass between them, like a shortcut. I can model that here, with this sheet of paper. If I fold the ends and connect 2 points, I can take this pencil and shove it through to connect them. And I stick this pencil through it. And I stick the pencil through it. And we stick the pencil through it. The pencil acts as a wormhole now, connecting two different points in spacetime. Transversal wormholes would normally collapse before anything could travel through them mouth to mouth. To stay open, they require a type of matter that doesn't interact normally with spacetime, referred to as
exotic matter.
Yeah, like he said. Wormholes in certain metrics, like the Schwarzschild metric, distort spacetime similarly to Schwarzschild black holes. That means some of the weird and wacky light effects you see around black holes also happen around wormholes, like gravitational lensing. See, the difference is, wormholes don't have a horizon. Instead of a dark emptiness, the light from the other mouth actually reaches your eyes, albeit distorted like a funhouse mirror, of course. Going back to our light cone of science. Going back to our light cone of science. Going back to our light cone of science. Different spacetime curvatures bend and warp the light cone. When the light cone tilts past 45 degrees, weird effects such as instantaneous movement in coordinate time, and even going back in time travel, start appearing. Wow, how would that happen? Let's go to our whiteboard of science and find out. Alright, here it is, our whiteboard of science. Give me a second here. Alright, sweet. The spacetime diagram shows how time travel is possible using a wormhole. Awesome, now take a look at this. If you were able to rapidly accelerate one mouth of the wormhole, it would experience time dilation. Time dilation! Time dilation! Remember? Now wormholes always transport objects based on the proper time of the mouths, represented here by the alternating colors and numbers. That means if you go through one mouth of the wormhole where its proper time matches with the other mouth's proper time in the past, you travel to the past.
A gateway to your own past, if you wish.
By changing the acceleration of one of the mouths, that's how curvy this line is here, you change how the proper times line up between them. Again, you can see that here by the slope between corresponding proper times. If it takes some time to travel through the wormhole, you can still create situations where the proper times match, corresponding to instantaneous movement in coordinate time. Now if it takes a while to travel through the throat, but but not too much time, slightly faster than light travel still occurs. And if it takes a long time, and the miles are relatively close, you can actually jump forward in time.
I'm sending you the cleaning bill, Mr. Wonka. Dry clean.
To demonstrate this, let's say I'm Thor with my mighty hammer, Mjolnir. Mjolnir? Mjolnir, currently residing in Asgard, when the Avengers need to assemble back on Earth. How do I get there in time? The Bifrost, of course. As a matter of fact, the Bifrost operates via a wormhole designed to transport individuals from Asgard back to Earth, and vice versa. Given that one mouth accelerates, Thor should actually be able to make it back nearly instantly. Pretty cool, huh? And please, consider the following. Now that we're here at a pool table of assignments, let's perform a thought experiment. Let's say we have a billiard ball, and it's on its way to a pocket. And for fun, the pocket is a wormhole. The wormhole leads to a different spot on the table, in the past. When the billiard ball exits the wormhole, what happens if it collides with its younger self, knocking it away from the wormhole? This situation is a paradox, because if its younger self never enters the wormhole, its older self can never exit the wormhole, and knock its younger self off the course, which is a contradiction. This paradox actually has a name, Polchinski's paradox. Let's see it live. So how do we resolve this paradox? What if instead, the original ball was never aimed at the wormhole, and instead the future ball knocked itself in? That would mean later the future ball exits the wormhole and knocks its younger self in, which would mean later the future ball leaves the wormhole and knocks its younger self in, which would mean later the future ball leaves the wormhole and knocks its younger self in, which would mean later the future ball leaves the wormhole and knocks its younger self in. Do you see what's happening here? This is a time loop, a closed time loop. This time loop is self-consistent and resolves the paradox. Let's take a look at this situation live. Thanks for joining us on our discussion on wormholes and their effects on space-time. I'll see you later. I've got a wormhole to catch.
Oh god, sorry I shook it. We're gonna have to do that again.
A wormhole is a thing that's not exactly my line.